Welcome, ladies and gentlemen, to Calculus BC. In today's episode, we will be introducing Polar Part 2, which is going to be a basic intro into polar graphing. And so, in order for us to understand polar graphing, what we're going to do is we're going to revisit some old trig functions, and I'm just going to do a few examples here. That way everyone can kind of see how this goes. So what I'm going to do is I'm going to start off with a polar graph. With a basic polar graph here, r is equal to 4 sine 2 theta. Now in the last video we discussed the idea of polar coordinates being written in the form of r comma theta, where theta was your input, which was always represented by an angle, and then your r was an output that was always a radius value. And so from here, when we're going to go graph 4 sine 2 theta, what you want to do is, especially in the beginning, is you probably want to do a rectangular version of the graph first. So the rectangular version is the version that you know from trigonometry from your integrated 3 class, where you would have y equals 4 sine 2x. Now you don't have to write the equation like this, but this is the rectangular version of it. And I'm going to graph this thing on the period from 0 to 2 pi, and I'll explain why I'm doing that in a second. But if you know your polar graphs really well, or your trig graphs really well, then you'll know that the frequency of the function is 2, which means on a period of 2 pi, you will have 2 of these sine waves. The amplitude is 4, which means it will go as far up as 4 and as far down as -4. This guy will end the period at 2 pi, halfway is pi, halfway between the halfway is pi over 2, and then 3 pi over 2 here. Now, one thing I'm going to do that is different than when I normally teach like an integrated 3 class or honors pre-calc is I'm actually going to find out the values of the humps, which is all the halfway between the halfways, halfway points. So 3 pi over 4 here, 5 pi over 4, and then 7 pi over 4. So let's talk about the anatomy of this rectangular function here and how it's going to eventually translate into our polar function. So remember, I call this y equals 4 sine 2x, but remember, y is the output here, and x is the input. And so I could almost see this as a theta axis and an r axis, if I really wanted to, for this particular rectangular function here. And so the reason why I decided to do that instead of x versus y is because I want you guys to understand that anything that's above the x-axis is positive radius value, and then anything below the x-axis is going to be negative radius value. Now, why is that important? Because when we talked about it in the last video, anything positive radius value, we dictated anything positive radius value as advancing radius. Anything that was negative radius value was retreating radius. So, in other words, advancing going forwards, retreating going backwards, depending on which way we were facing. Now, which way we were facing is dictated by the angle. So, let's see if we can put all of that together and graph a polar function. Now, I'm going to use a very particular type of graph paper on this one. This one here, yes, I am cheating, and I am cheating on a couple of levels. One, I have all of the radians already labeled out for me. That was actually unintentional. I am unintentionally cheating here. The reason why it's helpful is because now I know which way I'm facing at all times. The real reason why I chose this is because the radians here, the lines that are diagonal extending out from the origin, are divided into pi's over 12, which helps me see things a little bit more clearly. But I can actually post this thing on my Connect if you want to use the cheating graph paper. It's all good. Okay, so what I'm going to do is I'm going to say, all right, when my theta value is 0, my radial value is 0. So that actually makes a lot of sense here. My starting point is going to be right here. Now, as my graph moves towards pi over 4, its apex. Now, I'm hoping that everyone understands that at pi over 4, which is right here, my maximum radius happens. That's going to be 4 radii long. So I'm going to go 4 circles out. So 1, 2, 3, 4. That's right here. Now the question is, how do I get to that? How do I get to that radius? Do I just go extend out like that? Do I do something other? Do I do something else? Who knows? Well, from here, I'm hoping if I just do one semi-quadrant of this, then this will make sense. If I go to pi over 6, that would be a value of 2. So if I go to pi over 6, that's a value of 2 radii, so 1, 2. And then pi over 12 is going to be half of that. So I'm hoping that it makes sense that as your pendulum, not your pendulum, but as your spinner spins up towards the pi over 4, your radius value will extend out in a circular fashion towards that pi over 4. As you move from pi over 4 to pi over 2, it's going to come back down. Your radial value will shrink until it becomes 0. So as you approach pi over 2, your radial value will shrink towards 0. And that's what creates this first little flower petal type figure. From here, you're going to rotate. Your character will spin until 3 pi over 4. Now, 3 pi over 4 has a value of -4, a radial value of -4. Now, because your radial value is negative, when you are facing the 3 pi over 4, and I circled that for just a second, you're going to be retreating, which means your second petal's radial value will actually show up in the 4th quadrant. And it's going to, and if you follow the other, if you start plugging in certain numbers, what you'll find is that it will extend out this way. Like that. Now, as I'm doing this, here's what I'm not doing yet. I am not throwing down the direction of growth, and I want you guys to get used to throwing down the direction of growth. I just didn't do it because I didn't want to switch colors, but now I'll go and switch colors. There we go. That's our second petal. Now from here, the third petal. How do I get to the third petal? Well, I moved all the way to pi, which is a radial value of 0. And now, once I'm facing pi, I'm going to turn, my character will turn towards 5 pi over 4. 5 pi over 4 is out here. My character is turning this way. Right now my character is facing 5 pi over 4. My radial values are positive, which means I am advancing. I am advancing towards that 5 pi over 4. And then as I approach 3 pi over 2, I'll jump back in. And again, if I wanted to put the arrows, I will put the arrows. In fact, I really want to put the arrows in there, and so do you. And then as you guys can see what's going to happen is, as I face 7 pi over 4, I'll be facing the 4th quadrant, but I will be retreating, and then I will be retreating back towards the 3 pi over 4, which is right here. And then I will close it back up like this. And there you have it. That is your first flower petal sine curve. Now what I'm going to do is I'm actually going to label the petals in order. So this was 1, this was 2, this was 3, and this was 4. Now understanding the direction of the growth is actually really important, especially in the next example, when we look at a circle that almost duplicates itself. So let me go ahead and scroll down, and I will take care of this circle. And I will explain why the circle and understanding the direction of growth is really important. So r equals 6 cos theta. Here's our next example. So again, I'm going to do two versions. I'm going to do a rectangular version, a rectangular graph, and then I'll go ahead and do a polar graph. Polar graph, I'll go and throw it on the graph paper right now. We will use him in a little bit. So the rectangular graph, again, I'll go ahead and just throw this down here. This is theta and this is r. 6 cosine. Again, I'm going to go and graph on 0 to 2 pi. I forgot to explain why I graph on 0 to 2 pi. 0 to 2 pi is one full rotation around the unit circle. So whenever you do a rectangular version of your function, you want to graph between 0 and 2 pi because that is one full rotation around the circle. So that is why we did that. From here, this is going to be pi halfway here and 3 pi over 2. I'm hoping that you guys are getting really fast at graphing those trig functions. Again, it's been a long time since we've done it, but it's not a huge deal. 6, -6. It's not a huge deal that you are struggling with it. You need to be able to do it. Sorry. It is a huge deal that you know how to do it. Okay, so the radius is 6. So I'm actually going to see 1, 2, 3, 4, 5. Okay, excellent. I have enough radii for that. If you don't have enough radii, what you can do is you can just scale them up by 2, kind of like what we do on graphing. Okay, so from here, when I begin, when I'm facing 0, when my radian value is 0, I am out 6 spaces. Remember, we always start off facing to the right, when we're doing 0. So I'm going to go out 1, 2, 3, 4, 5, 6. This is my starting position here with cosine, because when my angle is 0, my radial value is 6. I am now going to move in towards pi over 2. I'm going to move in towards pi over 2 this way, and as I approach pi over 2, I'm going to go what we call tangential to pi over 2 because my radial value is 0. As I face pi, I'll be retreating in radius, and I'll be moving towards -6. But remember, if I'm moving -6 but I'm facing pi, then I'm actually heading back out towards where I was to begin with. And there we go. That is the first half of the graph. Now, as I leave pi, I will be heading towards 3 pi over 2. As my radius spins towards 3 pi over 2, my radial value goes towards 0. So I'm going to go ahead and switch colors here for a second into something that we can see. And then I will head towards 0. Now, I know red and purple don't exactly contrast each other that well. But as you can see, what's happening is as I cycle one more time through my cosine function, as I cycle through one more time on my cosine function, the circle will overlap itself. So you can almost see this. You can almost see this as the first circle and then the second circle. Now, why is this important? Why was this example necessary? It's because at some point, we're going to be finding the area of these functions. And if you use the limits of integration from 0 to 2 pi, you will end up with way too much area. In fact, you'll end up with double the area. So it's important to know when a function overlaps itself, especially in polar, especially when we encounter something in a couple minutes called the limacon. When something doubles on itself, you want to make sure you subtract the area that you don't want. And I think that's going to be where I close up this video. It's getting a little long in length. And so I will make a second video about polar graphing where we will investigate the cardioid, the limacon, and the lemniscate. And I will see you in that episode.